All right, so we'll be starting out here with alchemy and atomic models, a little bit of kind of history of the atom. Now, since you don't have the notes package yet, I do have the notes for this lesson photocopied for you, so I'll pass those out here. All right, so when you print off your notes package, it's not going to look like this with the PowerPoint slides in there, but every lesson will start out with the key points. So there'll be a title, which will be the lesson number and name, and then the key points of that lesson. The key points are the things that I'm probably going to test. Those are the things you're going to want to be watching for as we go through. Okay, it's always a good idea to highlight, underline, okay, make some notes in the margins, things like that when I talk about those things, because obviously your notes package is important, but sometimes I go beyond that. All right, so if I go and I start, talking about something that's related to that, it's usually a good idea to write down the context of an example that I go over. Like if I'm talking about an example that involves somebody in a hang glider, okay, what I usually do when I do a unit exam is I go back over my podcast and go, oh, I went off on that great tangent about the guy on the hang glider, and I make up a question on the exam about a guy on a hang glider. Okay, and so it's always a good idea to kind of go over those little examples, okay, things like that as we're going through. Okay, and obviously you can always review those in a podcast. Okay, if you wrote on your notes, he talked about some guy in a hang glider, go back to the podcast because it'll have the same lesson number and name, and scrub through until I've got a picture of a guy hanging from a hang glider. You might not be able to tell because I can't draw very well. It'd be like a stick person under a line or something. But okay, and then kind of listen to that example again as a way to review. All right, so the key points for today, we're going to look at how the theories of the structure of the atom were developed, okay, and we're going to hopefully review, okay, the parts of the atom and their characteristics. What are the three main parts of the atom we're going to be most concerned with? Everybody remember them? Proton, neutron, electron. Okay, so those are the big three. Okay, obviously two of them are found in the nucleus and the other is not. Okay, we'll talk about that. Okay. So, alchemy. Okay, what's alchemy? Well, alchemy was what people did before there was real science. Okay, alchemy was a lot of trial and error, and if you can imagine, the kind of mad scientist laboratory, with all the bubbling potions and things like that. That was alchemy. Okay, there were people who were trying to do things that we now know to be impossible. Okay, they were trying to do things like turn lead into gold. Right? Which is impossible because lead atoms and gold atoms are different, and you simply can't turn one atom of something into another. We know that now because we have a better understanding of chemistry. Okay? These guys were trying to do things that would essentially get them rich, right? But they didn't carry out really true scientific experiments. They mixed a couple things together, and when it didn't work, they threw it out. Okay? If it worked, then they did it a couple of times and made some notes on it. Okay? But it really wasn't, well, I've got this hypothesis that I want to investigate. I'm going to manipulate this variable, control these variables. It was, hey, let's pour this crap together and see what happens. Okay? I mean, I'm sure that a lot of alchemists had very short lives. Okay? There were probably a lot of alchemy labs that blew up, okay, as a result of some of the things they were doing. All right? So in that said, they still discovered a lot of important things about the behavior of matter. Okay? And a lot of that carried over when the scientific method was developed. Okay? And a lot of that was used to build the kind of fledgling science that became chemistry. Okay? All right. One of the earliest atomists, okay, that's a person who thought that matter might be made of tiny little particles, okay, was this Greek guy named Democritus. Okay? And he said, I think that honestly it seems like that all matter should be made of tiny little particles. Just seems like, the way things work and the way things behave, that kind of makes sense. And of course, back at the time of the Greeks, that was about all they would have to go on. He had no real way to prove that. Okay? And his idea wasn't really well accepted. Reason being, other guys like Aristotle and Plato, they said that everything was made of 4 elements. And what were the 4 elements? Earth, air, fire, water. Okay? And that made a lot more sense to people because they could explain a lot more with those 4 elements. Okay? For example, like lava, for example, was some parts earth and some parts fire. Kind of made sense, right? I mean, it came out of the earth and it was hot and it destroyed things. Okay? So that kind of made sense. Steam was some parts air and some parts fire and some parts water. It made sense. You had to add those 3 things together to make it. Right? So these were things that they could explain, they explained how stuff behaved a lot better than tiny little particles that moved around. Okay, so Democritus' idea of the atom wasn't well accepted, even though it was right, because he had no way to explain or prove it, and he wasn't as well respected as Aristotle and Plato were. Okay, so his idea kind of got thrown by the wayside. Now, it wasn't all bad for Democritus. He came up with something else that was pretty good. No, democracy, hence the name. Yeah. So it wasn't all bad for Democritus. He did come up with some good ideas. Okay, that was his kind of claim to fame. But he had a good job. Being a thinker in Greece, which is what he was, Plato, Aristotle, those guys, they were thinkers. Okay, that was a sweet gig to have. You got to sit at the Acropolis all day, and people would fan you with big palm branches and feed you grapes, and you just had to come up with ideas. Okay, if you were going to get a job, that was the best job to have. Okay. But his idea wasn't taken seriously for about another 2,000 years, okay, when a guy named Dalton came up with the atomic theory. Now, during the Middle Ages, okay, that's when the alchemists were doing all of their work. So it's kind of like Leonardo da Vinci's workshop here. He would have kind of been an alchemist. Okay, so he had lots of the flasks and beakers and things like that, and mortars and pestles and all things that look like witchcrafty kind of. Okay, that would have been kind of what alchemy was all about. Okay, and they did come up with, they did discover a lot of things that did, like I say, carry on into the fledgling science of chemistry. These two guys turned alchemy, into a real science. Okay, Antoine Lavoisier and Roger Bacon were the guys that essentially came up with the scientific method. Okay, how do we test ideas in a controlled fashion? Right? How do we run a controlled experiment? Well, we come up with a problem. Okay? That's the problem we want to investigate. Okay? We come up with a hypothesis. Okay? If this is the cause of this thing, and I do an experiment like this, then these will be the results. Okay? That's a good hypothesis. And then, okay, I'm going to manipulate this variable. This variable is going to respond to that manipulation. I'm going to control everything else that could affect it so that I know exactly what the effects of this change were. Okay, that's the scientific method, running a controlled experiment. Okay, everyone follow me there? All right, so rather than just, oh, well, I mixed those two things together and I didn't blow myself up, so that didn't work. Okay, that's not science. Okay, that's blind luck. All right, so they were important essentially in developing the initial kind of chemistry. Now, the idea of the atom. As people watched chemical reactions happen, okay, they started to realize where alchemy was going wrong. Okay? Again, the alchemists were trying to do things like turn things that were common and cheap into things that were rare and valuable, like lead into gold. Okay? Well, we can't do that because now we understand what atoms are built out of. Okay? An atom of lead is way different than an atom of gold. And I can't change the structure of an atom. Right? If I look at, let's say, well, let's use our two examples here. Lead, for example, on the periodic table, okay, it's got 82 protons. It's got well over 100 neutrons. It's got 82 electrons. Whereas gold, okay, has 79 protons, way fewer neutrons, okay, and 79 electrons. They're different. I can't just magically take away 4 protons, okay, or 3 protons from lead and turn it into gold. Okay? If I change the nucleus of an atom, what have I done to it? If I take part of it away? Well, I've manipulated it, but I've also split it. Yeah, exactly. That's nuclear fission. I can't change the nucleus of an atom. Changing the nucleus of an atom involves one of two processes. Fission, kaboom, or fusion, kaboom. Okay? They're both bad. Right? You can't change the nucleus of an atom. You can change the number of electrons. That happens all the time. But you can't change what's in the middle. Okay? Changing that would change what it is, and we just simply can't do that. At least not at that kind of level. We can split atoms, but there's, drastic side effects to that. Okay? We can fuse atoms. That's what the sun runs on, fusion. Okay? We'll talk about that in a few minutes. All right? So basically, what they discovered was during chemical reactions, when you mix two things together, in the end, you had stuff that was different, but it was still made of the stuff you started with. Okay? So as an example, you could mix vinegar and baking soda together. Okay? We've done that lots of times in our life probably. Okay? Okay, whoops, sorry, that's not the right stuff. Sodium hydrogen carbonate. HCO3. Okay, so when you have this reaction going on, okay, on the other side of this reaction you get water, you get sodium acetate, okay, and you get carbon dioxide. Certainly these look a lot different. One's a gas, one's a clear liquid, one's a white solid. Okay, when I started out I had a white solid and a smelly clear liquid, right? But if I look at all the atoms that I have on both sides, I have the same stuff that I started with. Okay, I have acetate. Okay, I have hydrogen. Okay, I have oxygen. Okay, got some of it from here. I've got carbon and oxygen together, which I also got from there. Okay, I still have the same stuff that I started with, and that's what chemistry started to reveal, is that no matter what you mix together, you're not changing what you have. You're changing who they might be paired up with, but you still have the same elements. Okay, and that's actually where the term element came from. The elements didn't change. The elements of your reaction are still the same. All right, who they end up with changes. Right? But to an alchemist, when they mixed stuff together and it went kaboom or it bubbled and fizzed, they were like, look, it's magic. I changed it. Okay? And they had this idea that they could change one material into another, okay? Which they weren't really doing because they didn't see what was going on at an atomic level. Okay? All right, so when I have a chemical reaction, I still have the same atoms that I began with. Okay? I can't change what's in here. Okay? I'm still going to have these protons, these neutrons. Right? I can just change who they go with. So an atom then is the smallest particle of an element that still retains the properties of that element. Okay? If you could conceivably cut something down and keep cutting it until you couldn't cut it anymore, what you'd be left with would be atoms. Now luckily you can't do that with a knife. Okay? You can't split the atom with a knife. That would be bad. Okay? If you're cutting carrots, you'd have a mushroom cloud in the kitchen. Okay? You can't do that because a knife is millions of atoms thick, even on the sharp edge. Okay? So you're not splitting any atoms at that point. Okay? We couldn't actually cut something down that low, but if you could, okay, you would get to the point where you simply couldn't cut it any smaller and have it still retain those same properties. All right? If you split an atom, it's different now. Okay? It's no longer, let's say, if it was uranium. It isn't uranium anymore. Okay? It's going to be some lead, and it's going to be some other atoms that get produced, some free neutrons floating around, okay? Things like that. You physically change that atom. Right? That's what, but it requires perfect conditions, essentially, for that to happen. Right? And, of course, it creates a lot of unpleasant byproducts. Okay. All right, so Dalton's atomic theory went like this. Dalton watched a lot of chemical reactions, and this is where he got his ideas from. Okay, first off, he took Democritus's idea and he ran with it. All elements are composed of tiny, indivisible particles called atoms. Okay, because Dalton was before the atom was split. Okay, at that point, it was thought that you couldn't make atoms break in half. Right? He knew that in chemical reactions, atoms always stayed together. Okay, and that they could switch partners, but that they never changed. Okay. To that point, atoms of the same element are identical. If I have 5 oxygen atoms sitting side by side, it would be like looking at pentuplets. Okay? They would be exactly the same in every way. I would not be able to tell them apart. They all have the same number of protons, they all have the same number of neutrons, same number of electrons. Okay? They're all identical. And then, of course, if atoms of the same element are identical, atoms of different elements are different. Okay? So all atoms of oxygen have 8 protons. All atoms of carbon have 6. Okay, they're different. It's that number of protons that gives them their certain physical properties. Okay, atoms of different elements can combine with one another in simple whole number ratios to form compounds. Okay, so this is how compounds are formed. Atoms go together. Now, what do they mean by the whole number part? Right, you can't have half an atom. If you did, you split it somehow. All right, so if I'm making water, for example, water is H2O. That's 2 hydrogens and 1 oxygen. Okay, I don't reduce it down and go H1O.5. Okay, it's the same ratio, but I don't know what half an oxygen atom looks like. Okay, because half an oxygen atom isn't oxygen anymore. That would mean it only has 4 protons. That would make it beryllium. Okay, that's not the same thing. You can't have half of an atom in a compound. They always go together in whole number ratios, 3 to 1, 3 to 2, 1 to 4, whatever it happens to be. Okay, but they always go together in whole numbers because atoms can't be broken up in a chemical reaction. Right? Everybody follow me there? That's essentially what he's saying in 3 and 4. Chemical reactions don't change the atoms. They change the compounds. They change the partnerships that go on, but they don't change the materials, which is what I showed you with the vinegar and baking soda example a minute ago. Okay? Chemical reactions occur when atoms are separated, joined, or rearranged. Atoms of one element are not changed into atoms of another by a chemical reaction. This point here was the death of alchemy. Okay? He basically said, you're never going to transmute lead into gold. Okay? You just can't do it. Atoms don't work that way. All right. His atomic theory's got 4 points. Is that something I might test on a quiz? It would be easy multiple choice question type of material on a unit exam. Right? Which of the following is not part of Dalton's theory? You have 3 of them that are and 1 that isn't. Okay? So make sure you know the points well enough that you could recognize them, okay, as being correct or not. Okay, questions there? Now, when Dalton came up with this theory, people said, well, that's wonderful. Things are made of tiny particles. What do the particles look like? Of course, when Dalton was around, people didn't know about protons, neutrons, or electrons yet. Okay, so he had to come up with a model. And that's problematic because atoms are really, really small. Okay, nobody knows what they look like. We have a pretty good idea now, but we still can't really see individual atoms. They're incredibly tiny. Okay, so he had to come up with a shape, something to represent an atom. Seemed like spheres were pretty common in nature. Okay, stars were spheres, planets were spheres. Seemed like a pretty common shape. He said, I think the atoms are a solid sphere. People went, okay, you're the boss. Okay, there was no one around to prove otherwise. They were too small to see. Okay, we'll go with that. Okay, but as people started performing other experiments, the solid sphere model started to not hold water anymore. Okay, it started to have some pretty noticeable flaws. One of those flaws had to do with what happens to charges in certain kinds of reactions. Okay, we use batteries, especially rechargeable ones, for so many things nowadays, and all that is a chemical reaction. Okay, a chemical reaction that releases electrons from one material and sends them to another. We intercept them between the two materials and use them to power devices. Okay? People were doing experiments with electrochemistry early on and noticing that charges would flow from one material to another. Well, there was no way to explain that with this model because it didn't have any what? Yeah, it didn't have any flow and it didn't have any charges. There weren't any negative parts or positive parts in this model. So it didn't explain that. So they said, you know what? Atoms aren't a solid sphere because then where are all these negative charges that we're intercepting in a chemical reaction coming from? Is the atom getting smaller? It can't be getting smaller because the mass isn't changing. Okay? So they knew pieces of it weren't essentially breaking or things like that. So they had to come up with a new model. Okay? So that new model was proposed by J.J. Thomson in 1897. Okay? It was called the Plum pudding model. He said, I'll go with the sphere, and I'll say that the sphere is positively charged because positive charges didn't move in the reactions, only negative ones. Okay? And he said, the sphere is covered with these little negative charges, and they can fall off. And that's the ones that I'm intercepting that are moving around in a chemical reaction. Right? So it was plum pudding. The plums were the electrons, and the pudding was the central mass that was positively charged. Okay? And people accepted that because it explained what was going on. It explained where these electrical charges were coming from. He said, well, and a good name for those electrical charges is going to be electron. Okay? So that's where the name came from. We still didn't have any protons or neutrons at this point. There was just this solid mass that was the atom, and then these little electric particles that could fall off. Okay? Everybody with me there? Okay, so that seemed to fit for a while. Okay? But this is the start of the nuclear age. Okay? Just after, like 1920, okay, that kind of timeline, people started doing a lot of experiments with nuclear materials. Unfortunately, those scientists had very short careers and lives, okay, because they were always playing around with stuff that was radioactive. Okay, they had no idea, of course, at the time that was bad for you. Okay, I watched a documentary on the Discovery Channel the other day, and it was showing Henri Becquerel's desk. Henri Becquerel discovered X-rays, and his desk is in a museum, and if you run a Geiger counter over it now, 100 years later, it's still hot. Okay, still radioactive, because he had these pieces of like uranium and stuff in the drawers for a long time. So he was like getting 50 chest X-rays a day from his desk. Yeah, wasn't it? So him and like Marie Curie and people like that, they had very short careers because they got cancer from all the radioactive material they were working with, because they didn't know that there was these invisible beams essentially coming off of all the rocks that they had, and it was really bad for them. Okay, but all of those experiments led people to understand that this model didn't hold up either. Because if there were these pieces coming off that weren't electrons, there had to be other pieces involved. Okay, because when something is radioactive, the atom actually breaks on its own. Okay, that's what produces the radiation and the energy. So protons and neutrons come off of this atom, and they collect, they form other things. Okay, but this model didn't explain that because those things weren't included in it. Right? So people started coming up with all kinds of different models. Okay? For about 20 years, there was probably 5 or 6 accepted models of the atom. Some saying, we'll go with the solid sphere, but we'll say that there's these 3 different chunks on it. Okay? Or there's these things in here, and the electrons orbit like planets around the sun, or they orbit randomly, or they do all these things. No one could really come up with a good explanation. People still liked the idea of a sphere. They wanted to keep that. Okay, so most of the models looked a little bit more like this one here, okay, until a guy named Rutherford came along. Okay, and Rutherford designed this experiment to prove once and for all whether the atoms were solid objects or whether they contained a lot of empty space. Okay, so he set up an experiment that looked like this. Oh, I'm not there yet, but we'll get there. Okay, so Thomson, this is just comparing here. Thomson had the plum pudding model, okay, so it looked like this. Rutherford and Bohr had this idea of a nucleus and then electrons around the outside, okay. Rutherford's model, actually, he preferred this idea where electrons were all the same distance away, but they were offset slightly, okay, with a nucleus in the middle. Okay. So protons, neutrons, and electrons couldn't float about because they never moved in chemical reactions. So they had to be somehow stuck together. Okay? That's what led to this idea that there could be a nucleus. So Rutherford's experiment went like this. He had a source of alpha particles, like an X-ray machine, okay? And he had a piece of very thin gold foil. So imagine like tin foil, but made out of gold and even thinner than that. Okay? So it was only a few atoms thick, this foil that he had. Okay? And he said, if atoms are solid spheres, when I shoot the particles at this paper, they'll all bounce back because there'll be no way for them to get through. But if atoms are made of a nucleus and surrounded by a lot of empty space that's basically filled up with electrons, which are tiny, a lot of the stuff is going to go through. In fact, almost all of it will go through, and it'll be detected over here. Right? So what he had set up was essentially like photographic film, kind of like when you get an X-ray. Okay? They put essentially a piece of photographic film behind you. You stand in front of the X-rays. Your bones reflect the X-rays, but the rest of it goes through and exposes the film behind. Okay? Follow me on how that works. I know you guys are from the digital film era, or digital camera era, so you probably never had a camera that you had film in. Okay? But they used to have film in them. Okay? That's what he had behind. So he fires up the X-ray generator here, shoots the beam of particles through, and he gets some stuff behind. He had predicted all behind. He predicted that atoms, the nucleus was so small that basically everything would go through. Right? But what he found was some of it was getting deflected. Some of it got through, but a lot of it was deflected, and he was getting these little exposure points all over the place. So his diagram ended up that, yep, electrons, they have this cloud. There is a nucleus, but the nucleus is bigger than I thought. And it's big enough that sometimes those particles were hitting it, and getting bounced over in a certain direction, deflected at an angle. Yes, lots got through. Okay, that proved that there was a nucleus, okay, and a lot of empty space around it, but the nucleus wasn't as big as he thought it was. Okay, it was bigger. Sorry, it was bigger than he thought it was. And he said this experiment was like shooting a artillery shell at a piece of paper and having it bounce back. Okay, he said I couldn't believe that atoms, that the nuclei of atoms were as big as they actually are. Okay, that as many particles got deflected. So this experiment proved once and for all there is a nucleus surrounded by a lot of empty space. Right? So all matter is a lot of empty space. Okay, it's just that atoms are really small. Okay. All right, so Rutherford, he's pretty important. Okay, Rutherford developed essentially the nuclear model of the atom. Okay, he said that it has a central dense nucleus. Possibly most important experiment that there was in physics to that point. Rutherford's discovery of the nucleus is what led to the nuclear age. Okay, the development of nuclear energy, nuclear weapons, okay, things like that. If there is a central dense nucleus and it's big enough to hit with other particles, then if we hit it hard enough with big enough particles, we can break atoms apart. That was the idea behind nuclear energy. Okay? There has to be a lot of energy that gets released when atoms are broken. Single atoms, no. If I was to split a single atom, you'd never notice it. Even if I split 100 atoms, you'd probably never notice it. Okay? Atoms are really small. But if you break a lot of them, all at the same time, you can get a lot of energy released. Okay? And that's what happens in a nuclear reactor or a nuclear bomb. Okay? In a nuclear reactor, you have a source of particles, a particle gun, okay, that shoots particles at fuel rods. On fuel rods are fuel pellets. Okay? These pellets are made out of usually enriched uranium, so really concentrated uranium. Uranium atoms are huge for atoms. They're still tiny, but they're huge for atoms. Okay? A uranium atom, okay, has around 240 particles in it. Okay? 92 protons, the rest being neutrons. It's a big atom. The bigger an atom is, the less stable it is. That's why uranium is radioactive. It actually spontaneously breaks down on its own, right? Slowly. We can make it happen faster. And when we make it happen faster, we get lots of energy out of it. Okay? Plutonium, similar. Okay? Plutonium's also a big atom. Okay? Has 94 protons. Okay? Around 244 total particles in the nucleus of the atom, so lots of neutrons. The more neutrons you have, the more unstable the atom becomes, okay? The more radioactive it is. That's why, and I don't know if you guys saw this, but the other day they were saying they had filled in the whole bottom row here of the periodic table. They discovered all the other atoms that fill that in, okay? The reason it took so long is they don't last very long, okay? They're so radioactive and so unstable that they decay down into other more simple atoms in a matter of hundreds or thousands of a second. Okay? They have to have a spectrometer there when they make the material so that they can capture its signature before it's gone. Right? So these atoms do not exist in nature. Okay? They have to be man-made. Right? So any of the ones on the periodic table that have just their outline, okay, that aren't a solid, those are man-made. They don't exist in nature. Okay? They're produced in nuclear reactors or at the Large Hadron Collider, okay, in places like that. All right, so back to this idea here of how a nuclear power plant works. So we shoot particles at these fuel pellets, and the uranium atoms break. Okay, so at an atomic level, what we see is, okay, an atom, okay, that gets hit with something, and that atom breaks into many pieces. And the pieces go off and break other atoms that are nearby, and it starts kind of a chain reaction. Right? That releases lots and lots of energy. In a nuclear power plant, we control how much energy is released by only exposing a certain amount of the fuel rod to the particles that we're shooting at it. Right? That way, it doesn't get too out of control. Right? What that essentially does is heats the water, okay, that this fuel rod is in, and the water turns into steam, and the steam turns a turbine, and we generate electricity with it. Right? That's essentially how a nuclear power plant works. If something happens and the fuel rods can't be removed or too much of them is exposed, it gets too hot, the water all evaporates, and we have a meltdown. Okay, that's what happened in Chernobyl. Okay, they had a meltdown, it overheated, the containment unit cracked, and all of the radioactive steam was released into the environment. Okay, and it, there's all kinds of radiation around Chernobyl to this day, and there will be for hundreds of years. Okay, it's a bad thing to have a nuclear accident. Okay, in a nuclear bomb, you want the reaction to go out of control. So you don't have little pellets that are exposed to only a certain amount of particles. You have some high explosive. You make a container that's more symmetrical than that, okay, out of high explosive, C4, plastic, something like that. And in the middle, you put a big chunk of fissionable material, plutonium, okay, something like that. And you detonate the explosive. Because of the shape, the explosion all goes in. So there's a whole bunch of particles that rapidly move in to this highly fissionable material and cause it to start splitting. And when it splits, pieces of it go off and split other pieces, and you get this chain reaction that ends up in a giant mushroom cloud. Okay, kaboom. All right, I just told you how to make a nuclear bomb. It's not really that simple. There's a little more to it than that, plus you can't get your hands on that kind of stuff for some reason. There's crazy people out there who would build one. All right, does that make sense to everybody? Okay, so atoms generally stay together. If I change the structure of the nucleus of an atom, I make other materials, okay, and I release the energy stored within the atom. In the nucleus of the sun, we have a different kind of nuclear energy that's going on called fusion. Okay? Fusion is more difficult to produce because it usually involves large amounts of heat and pressure. Okay? The sun is gigantic, so it has enough gravity that in its core, hydrogen atoms get forced together because of the extreme gravitational force. And so you end up fusing two atoms together to make a bigger one. And when you do that, you release lots of energy, more than fission releases. Okay? So fusion is even more energetic than fission is. Okay? And it keeps making different material. So we fuse 3 hydrogen atoms together and we get an atom of helium. Okay? So we make a different atom. Anytime you change the nucleus, energy gets released. Okay? Whether you're fusing it or splitting it. Okay, so we use typically the big atoms for nuclear fission. They're a bigger target and they're less stable. It doesn't do any good to shoot particles at tiny atoms. You're not going to hit them, and even if you do, they're probably not going to break. Okay, and they're not, even if they did, they don't release very much energy because they're small. It's better to hit big stuff. All right, so later on, after Rutherford's experiment there, proving the existence of the nucleus, then people said, all right, what's going on with the electrons? Okay. Obviously, the electrons are not in the nucleus. They're small and they move. And we know that they have energy. Okay, so they said, what's their arrangement? And that's kind of the argument even today is still, what's the arrangement of electrons? What are they doing in the atom? We know that they can change. We know that they can leave an atom and go to another. Okay, during a chemical reaction, that's what happens. Electrons move from one atom to another. So what do they look like? How are they arranged? Bohr came up with kind of the simplest. He said they orbit like planets around the sun. Because electrons are negative and the nucleus is positive, they're kind of held in place by this electromagnetic attraction, okay, and they orbit, right? It's not perfectly like planets because 2 or more electrons can occupy the same orbit, right? And he said that when an atom gets energized, electrons can pop up to other energy levels, okay, and then they can move back down. And people generally accepted that, except that we've now found that for the most part, atoms move in patterns other than circles. Okay, so while if you took a picture of an atom, it might kind of look like this at any one point, an atom is always changing. Okay, at least its electrons are always moving and thus changing. So this would only be an instant in time as opposed to always. Okay. So a guy came along and he said, electrons move in an area called a cloud. And they're like, well, it can't be that random. You can't just say they're all over the place. Okay? We know that they have certain behaviors to do with energy. Where are they all the time? And he said, well, they're in places called orbitals. And these orbitals have certain shapes, but electrons can leave orbitals, come back, jump to higher energy levels, different orbitals, come back. Okay? And that's why we see plants able to carry out photosynthesis or glow-in-the-dark materials. Okay? These both harness electrons moving from one energy level to another. Okay? How many of you have, like, on your watch, if you put it in the sun and then you put it in the dark, it's got parts that glow? Anyone here got? Yeah. Sometimes. I mean, it's not as common as it used to be because most of the time now we're just working on battery. But if you have glow-in-the-dark materials that glow for a short period of time, okay, the electrons get excited and they move away from the nucleus. They move from low-energy orbits or orbitals to higher energy ones. And then when the light goes away, there's nothing to keep them there. They need energy to stay up there, and they don't have it. So they fall back down, and when they fall back down, they give off the energy they had absorbed as light. So that object glows until all the electrons have fallen back down to lower energy levels. Okay? Plants do the same thing. When light hits a plant, the electrons in chlorophyll get excited, and they move to higher energy levels. And then at night, those electrons fall back down, and the plant harnesses the energy of the falling electrons to make sugar. Okay? So this kind of explained where the energy for photosynthesis came from. Okay? This movement of electrons from low energy orbits to high energy orbits. So basically, there's a cloud of electrons, and electrons can move throughout this cloud, far away, closer, depending on their energy level. They could be anywhere. Can we predict where they are? Yes. Okay? But if you take a picture of it at any one time, they could be anywhere. Okay? That's the currently accepted model of the atom, the de Broglie electron cloud model. Okay? So you might want to note, okay, that is our currently accepted model of the atom. Okay, questions on that? All right, so we got protons that are positively charged, we got electrons that are negatively charged, neutrons that are neutral. How can we tell how many of each are in an atom? Well, actually, it's the neutrons that can be different. Electrons and protons are always the same because an atom is neutral. So it has to have the same number of electrons, negatives, as protons, positives. All right? The number of neutrons is the weird one. All right? So on a periodic table, the atomic number tells us the number of protons and thus the number of electrons. So if we're looking at potassium, it has 19 protons. Okay? But number of neutrons, that's different. Okay? To calculate the number of neutrons, you might want to write this down. Okay, number of neutrons equals atomic mass, that's the number with the decimal in it, minus the atomic number. All right, so again, if we're looking at potassium, okay, we would take its atomic mass, which is 39.10, and we would subtract 19. Okay, so 39 minus 19, okay, gives us that there's 20 neutrons. Okay, now it does come out to a decimal. Can you have a portion of a neutron? No. You always got to round it. Okay, if it's greater than half, round it up. If it's less than half, round it down. Okay, that's going to be your number of neutrons. So it's atomic mass minus atomic number, and you're going to get a periodic table later on. Okay. All right, that's something I almost always ask, okay, on the unit exam. All right, so we got scheduled help here. Since this is your first day, you probably don't have anywhere to go. So what I'm going to do is I'm going to give you the questions that go along with this. You can work on those for today, and we'll go over them at the start of class tomorrow. Okay?